Okay, we're going to be talking about lines. And when people talk about graphing lines, have you ever wondered why we graph lines and what's the purpose? So the first thing we teach our students is like when you have something 2x plus 3 equals 8. You solve it. There are different ways of solving it. You can add, subtract 3 both sides. You could guess and check. You could say, let's try a number. How about 5 halves? And it turns out to work. Either way, you get down here and you get x equals 5 halves. Truthfully, you'll subtract 3 and divide by 2. But we're able to write the answer down. If we do something like this, 2x plus 3 is greater than 8. You get down here and you get x is greater than 5 halves. And if x is greater than 5 halves, you notice now we can't write down all the answers. So we graph them because there are a whole bunch of answers. Well, if I tell you something like x plus y equals 9. X plus y equals 9, well, you need two numbers to make an answer, first of all. So you have x equals 1, y equals 8. There's an answer. It makes it true, as long as they go in a pair. X equals 2, y equals 7. That's a pair. And so that's where we get a coordinate, meaning two numbers put together. 3 and a 6. X is 3, y is 6. Now we can't write all those down, possibly. I mean, if you think about it, you can have negative 2.3, 11.3. Tons, oodles and gobs of answers. And so in this case, we graph all these points. And all of those points are solutions to that equation. And that's where it comes down, just like this one. We've got here a graph of all of the points that will make this true. That's what a line is. And so you have various ways of doing that. So if you're going to graph a line, number one, you can take the line and you say, okay, let's just pick a number. X is 7, what is y? Stick a 7 right up there. 2 times 7 minus y equals 8. And now you have a one variable equation that's easy to solve. Piece of cake. So 2 times 7 is 14. Subtract 14 to both sides. You get minus y equals a negative 6. Y equals 6. So first method, pick and stick. You just pick a number, stick it in for one of them, solve for the other one, and you get an answer. It's the best way. One particular way of this, so that's kind of the first method, you'll notice, going back over here, you try numbers, you stick a 3 in there, you stick a 7.8, you stick 53 in for x, and you get these equations popping out that you have to solve each time. What if you picked a really nice number? A really nice number, like 0. 0 always gives you a really nice equation to solve. If you stick a 0 in there, 2x equals 8, x equals 4. So here we have, sticking 0 in for x, we are down at y equals negative 8. We stick 0 in for y, we get x is 4, and we're able to graph it without any problem. These are special. This is where they cross. This line crosses the x-axis, called the x-intercept. This crosses the y-axis, so it's called the y-intercept. So, first method, pick any point. Second one, pick really specific points. Pick 0, and you get intercepts. And so, in reality, you can think about the developmental process that would go with this one. Step number 1, pick a number. Stick it in for either x or y. Solve for the other one, graph the point. Then you'll repeat. Intercepts, pick 0 for x, pick 0 for y, stick it in, and graph. The other one is slope. Now, when teaching students about slope, we need to back up a little bit and make sure we know what slope is. Slope is not y2 minus y1 over x2 minus x1. I know that's the formula to get slope, but that is not what slope is. Slope is steepness. So we need to talk a little bit about this before we say how to graph lines with this. Slope is a measure of steepness. A couple of real-world examples that should come to your mind. 7% road grade. 512 roof steepness. Those are two main examples where slope is used a great deal. This actually means, if you took it like a cross-section of the mountain, just chopped it off, and there's the road heading up the mountain, that it would actually go 7 per 100. 7% is 7 per 100. This is where you get a ratio of how vertical you go compared to how horizontal. Same thing, if you have a roof that is like that, and it's a 512 roof, it means if you go 1 foot, that's 12 inches, horizontally you will go 5 inches up. Steepness is everywhere. Now, when we're teaching students, we will often have them say, okay, you've got 2.5 and 7.9. Find the slope between those. And we've never even told them the formula. That's really valuable to get the concept of slope in their mind before the formula ever exists. So, 2.5 right there, 7.9 right there. If you're trying to find out how steep that is, you need to find out what that ratio is. From 2 up to 7 is 5. From 5 up to 9 is 4. So the slope, 4 over 5. It just matches exactly what this is. 7 over 100, 5 over 12. So they get the idea of rise over run more than a formula that just drops out. So do that a couple of times, and then you can say, okay, so what's the slope between, say, what if the point's somewhere we don't know? 2.5? XY. How do you get the horizontal and the vertical? Well, what did we do last time? When we had a 7 here, it was 7 minus 2 was 5. So this is going to be x minus 2. This is going to be y minus 5. So the slope, even though we don't know what this point is, we can say that's y minus 5 over x minus 2. And then obviously the next step is, okay, find this slope. We have this random point xy, and we have another random point xy, but they're different. So call this guy the first point, and this guy the second point. So those are different numbers, the x1 and the x2. So here's x1, y1. There's x2, y2. The x and y on the first, the x and y on the second. And you were trying to find the slope and have them come up with the slope. You have, this is x2 minus x1. That's how you get that distance. This is y2 minus y1. So the slope all of a sudden that formula is not so scary to the student. Then when they understand this, all of a sudden it opens up their minds to how slope connects to equations, which is what we're going to come back to here. Certainly they can use this formula over and over and over again, but they need to know where it came from, that it really is how much vertical over how much horizontal. Now, when you start to go to equations, my suggestion, don't start off by doing this. Y equals mx plus b. Almost every algebra student can recite y equals mx plus b. They can't tell you what m or b are. That's bad news. It's meant to be a shortcut, a summary of the knowledge of the concepts that you have. It's not meant to be something that fell out of heaven and say, oh, here's a formula, now go and use it without questioning it. So, in particular, I do this. I say, find a couple of points. Stick in 0, stick in 3. So they're able to do this. If they've been doing pick and stick and intercepts a lot, they're like, oh, hey, I can do this. So they stick in 0. 2/3 of 0 is 0. Plus 5 is 5. Stick in 3. 2/3 of 3 is 2. Plus 5 is 7. Now I say, find that slope. So like, okay. And they may subtract it x1, y1, or backwards. They can flip it the other way. So 5 minus 7 is a negative 2. 0 minus 3 is a negative 3. And they get 2/3. And we do about 5 of those problems. And I say, okay, y equals 7/8 x plus 4. Can anybody tell me what the slope is? And there's got to be at least one person. And that's what you should be doing, is linking and saying, interesting. Huh. They're the same number. Again, you follow this process through. You say, okay, 0, you get a 4. Stick in 8, you get an 11. Find out the slope, and you get 7/8. They will get tired of this process. But if you keep drawing their attention to 7/8, 7/8, they're like, wait a second. So if I did y equals negative 2/19 x plus 11, my slope is negative 2/19. That is when they have finally produced this part of the mx plus b equation. They finally started to understand, yeah, if y is by itself, any number that is in front of x is the slope. And it becomes a shortcut, and they're like, ah, so I don't have to do this every time to find the slope. It's right there in front. So that is what allows slope to be helpful. For example, y equals mx plus b now becomes really, really useful to them if they truly understand that. Because you say, okay, graph this. Y equals 3/2 x plus 9. They can get a point, 0, 9. That becomes really easy. You're like, hey, wait a second. This guy is always the y-intercept. Now they understand, and you call this, so this guy always has a slope, and that guy is always an intercept. This is a slope-intercept form of an equation. And they understand that. That's important to bring out. So the 0, 9, they get that. Now, they could get another point to graph this. Or, if they know that the slope is 3/2, there's 0, 9, they know that the next point is up 3 over 2. And they can actually do it. Up 3 is 12 over 2. And that point will be on the line. That's how slope will help them. So that's kind of the history and development of how slope is actually a way to help with graphing. In particular, they are going to have opportunity to graph from something like that. 3x minus 2y equals 9. Now, most of them will not have had experience with standard form of an equation. In fact, many of you tutors will not have had experience with standard form of an equation very much. This is important to realize that, yeah, you can solve it, and you get y equals 2/3 x minus 9/2. Oh, slope is 2/3. Some people will like to say, oh, excuse me. When you solve it, you get 3/2 x minus 9/2. Now, some people say, oh, 3/2, something to do with the 3 and the 2. That'll come in very handy for them. But most of them will want to just solve for slope-intercept. The reason I keep doing this over and over is that when you are writing equations, of lines, you're going to be going exactly backwards of what you did here. Developmental process for graphing with slope. Find the slope, find a point. From the point, move up and over, and you draw your line. When you're writing equations, you have slope and a point. And you're going to use that to get your equation. Here, they were given equations, and they had to get their slope, get their points, and go forward. This, you're going backwards, and it should let you know, if you have the equation, you can certainly find anything else about the line. Here, we start with just a slope and a point. if you get an equation, you can get everything else. So a slope and a point is really all you need to know everything you need to know about the line. So, in general, this is what we'll do. Y equals 3/7 x plus 8. Here's an equation. Tell me what the slope is. Well, they'll say, oh, it's 3/7. Y equals 5/8 x plus 9. Slope is 5/8. Y equals negative 2/3 x plus 3. Negative 2/3. About this time, they'll start to get bored. They'll be like, yeah, I think I get it. And you're like, oh, really? Good. What if this was a negative 7/5? Give me an equation of the line. They'll say, oh, well, that must have come from y equals negative 7/5 x. And I'm like, well, how do you know what number it is? Yeah, it's a plus 19. Or minus pi over 3, or plus square root of 5. The slope only deals with this one. In order to get more information, you have to know a specific point that'll make it work. So in that case, I write up a few of them. I say, okay, which one of these, they all have slope of negative 7/5, which is a good opportunity to talk about parallel and perpendicular. But which one of these goes through this point? 5, 4. Now, this may cause them to reflect back and say, okay, so what does that mean? If a line goes through that, then this is a solution. This actually makes this true. And so try it and see if you stick 5 in for x, do you get 4? I'll do, okay, 5 times this, that's 5's cancel. Negative 7 plus 19, that's 12. Doesn't work. 5, 4, 5, 4. And then they get one that works. I'm like, aha, that's excellent. That's the line. That's how you know is whether or not that thing actually works when you put it in there. 5 times this would be a negative 7 plus 11. It's 4. Now, so in that case, slope goes in for m. Then you stick, so that's kind of the first step. Second step, you stick in the point. For x and y, solve for b. Now, I'm going to show you something that you may not be aware of. And you need to understand that some teachers will not want you to do this. Pay attention to support the teacher. If this teacher is only teaching the student slope-intercept, don't do this standard. But you may find this rather slick. You know, if we're going to do one with slope-intercept, if I said, write an equation of a line that has slope 3/7 and goes through the point 2, 11, process looks like this. Y equals 3/7 x plus b. Stick in the point. 2 goes there, 11 goes there. So 6/7, you have to subtract it from both sides. 11 minus 6/7. B is 71/7. Yuck! The complexity with the fractions, oh, not 77, 71. 71/7, the complexity with which you have to do the fractions gets cumbersome. So if their teachers taught them anything about standard or point slope or some of the others, go ahead and use those. But standard is really slick. I'll show you what I mean. We'll come to that problem in just a minute. Again, we're going to write the equation and the slope. So 5x plus 8y equals 9. If you solve that for y, you'll subtract the 5x over here, and you'll divide by 8. 3x minus 4y equals 10. Slope is going to be a positive 3/4. And so they start to see, okay, opposite sign 3/4. 6x minus 11y equals 12, positive 6/11. And you start to see the shortcut exist, and about the time they get tired of it, negative 7/9. And they're like, okay, so it had to have been a plus in there, so it was 7x plus 9y equals, and they're like, okay, so what number? Well, it could be a 12, it could be a 15, it could be a negative 3. This determines the slope. Just like in the slope-intercept, it was only the thing in front of x. Well, now, okay, which one of these points, give me another one. Oh, I already did that one. That's all right then. Okay, so which one of these points, which one of these equations goes through 3, negative 1? And you start to stick them in. You're like, okay, so you take a 3 there and a negative 1 there. 21 minus 9 is 12. 12 does not equal negative 3. Well, you can do it a bunch of other times, but you realize that's your baby right there. 3 goes in there. 21 minus 9 gives you a positive 12. And there you have it. Now, the reason that this is so handy, we're going to do that exact same one we had before. 3/7. That means we're going to have a 3x minus a 7y equals, stick the point in, 6 minus 77. It's a negative 71. You're done. There are no fractions ever. That's the beauty of having standard form. Now again, if the teacher is not teaching it to the student, it will be detrimental to bring this up to them. So don't do it. Just keep it with y equals mx plus b. But if not, you can always solve this for slope-intercept. Subtract that over and divide by a negative 7. You have y equals a positive 3/7 x plus 71/7, which is exactly what we had before. And you're welcome to take either path. That's why as tutors you're expected to know both standard and slope-intercept form of how to write equations of lines. Okay, so that's all for lines. Now, when we're dealing with systems of equations, when we're dealing with systems of equations, you know that there are two ways of doing it. You have substitution. Solve for one variable. Stick into other equation. And then solve for it. And then you're able to stick it back in and get it. For example, on this one, step 1, solve for one variable. The top is really a y equals 7 minus 3x. Step 2, stick it in. This y and that y are the exact same thing. They're both y. So that's y, stick it right in there. 2x minus 7 times 7 minus 3x equals 20. Now, students who have passed through the previous chapter know how to solve linear equations. This is something they've always done. Point that out to them. Once you get to this point, you only have one variable, and that's it. So, you have 23x equals, add the 49 over, you get 69. X equals a 3. You are not done. We are supposed to solve the system. Good point to bring up is that this has infinitely many solutions. This has infinitely many solutions. This is like a line shooting up. well, that one's a line shooting down, this one's a line shooting up, and there's one point that they cross, which means there's one point that will solve both of them at the very same time. This happens when x is 3. All you got to do is step number 4, which would be to find the point. Find the actual solution. So here, this only gave us half of an answer. You can stick it back into here, or you can stick it back into here. Either one will work. When x is 3, you get 9 plus what is 7? You get y equals -2. So we get 3, -2. That is the point where they both have it in common. So that was substitution. We're going to do the same problem. We're going to do it with elimination. Elimination is most valuable when solving for one variable is not easily seen. Elimination, it's exactly what it means. Get rid of a variable. One of them, 2, and you solve. For example, here, if we add these two things together, just add them, 3x plus 2x, that's 5x. Y and -7y is a -6y, 27. It doesn't help us, didn't get rid of anything. However, if we times this entire thing by a 7, so that it's exactly opposite of this, we get, what is that, by 7? 21x plus 7y equals a 49. Add them together, and that's where you get 23x equals 69, x equals 3. Plug this back in just like you did. Find the point. Now, elimination is most handy when you have 3 equations and 3 unknowns, or 4 equations and 4 unknowns. So, in particular, on this particular one, let's finish it out. Okay. So there is one set of x, y, and z that will solve both of these at the exact same time. And that's what we're going to do. Notice, first thing, get rid of a variable. In this case, we have 3 of them. So if we were going to choose to get rid of one, we've got to do it in 2 different ways, and you'll see why. Right here, I think the z's might be easiest. Doesn't really matter. So get rid of the z's by adding these 2 together. Now I'm going to erase these steps so you can kind of see how it goes. If you add those 2 together, you get 4x plus a 3y equals 8, and the z's gone. Now if you can get rid of the z in one more way, you will have 2 equations with 2 variables. So if we add these 2 together, but times that guy by a 3, so the z will be gone, we're going to have 9x plus 4x is a 13x. 6y and 3y is a 9y. And 21 and 5 is 26. Now we're back to 2 equations, 2 unknowns, just like we had before. Let's get rid of a variable. Y times this by a -3, and that'll get rid of the y's. This is a -12 plus 13, that's an x. -9 plus 9, gone. -24 plus 26 is 2. X equals 2. So we've solved it. Now we just come back and find the point. Stick a 2 in here, and we have 4 times 2. Subtract 3y equals 0, y equals 0. So now we have 2 of them. Take one more step back and plug them in anywhere you want. X is 2 plus 0 minus z equals 1. Subtract that over and you get minus z equals a -1. Z equals a 1. 201 is your answer. And you can check that in all of these. Stick 201, see if you really get 7, 201. In general, that is how elimination will help. Some of the teachers will not appreciate this type of notation. You can tutor them with however they've learned it, but this will be the basic developmental process for that. Okay, and the final one for this session is exponents. There are two major concepts that you need to understand about your students as far as what they have as a background when they come into the course. The first one is variables are fairly new to them. They don't understand variables representing numbers. Not fully, at least. And the other one is textbooks are written to make sure that they've written down everything correctly, but not necessarily in the best way for students to understand it. And that's where you come in. You get to interpret and bridge this gap between what the book writes down and what the students write down. For example, the book will write down as a law of exponents. They will say a to the m, a to the n equals a to the m plus n. Or they will write x to the m, x to the n equals x to the mn. Your students will not see this as the exact same thing as 5 cubed times 5 to the 8th equals 5 to the 11th, or x cubed to the 7th equals x to the 21st. For a student who is just learning variables, there are two variables over here representing, and they think about it, yeah, they represent two different numbers. There are two variables over there. In their mind, oh look, there are two different numbers. Over here, there are two numbers. There's only one number over there. Completely different. So we're going to go through how to organize exponents so that they can understand exactly what's going on. In general, the book will write this as a law of exponents. Then you turn the page and there's another law. And then you have this one. And then you have this one, just as a law. There's no reason, there's no justification. Why should a student believe that anything to the 0 power is 1? They're like, it should be 0, shouldn't it? Anything else? Oh yeah, or x to the negative n is 1 over x to the n. They'll say, this is a definition of a negative exponent. They don't tell you why that should make sense. And so we're going to cover all of these, and we're putting them on the same place, particularly because the book will have them all separately. And so when the developmental student opens up the textbook and they see 50 problems with x's and y's and parentheses and exponents, you may see all the same problem. They're just dealing with the concept of exponents. But they see, oh shoot, is it that kind of a problem? Or is it that kind of a problem? Or is it that kind of a problem? Or will I be using that law? And so we're going to put them all together for them to accommodate that discrepancy between them and the book. So, in general, the best thing for exponents is kind of, well, in education classes you'll learn it as an advanced organizer. It's just a table, and it will have rule y. So you just do a table. Now, for a student, when you write the rule column, it should be in the student's words. Learning is producing something. So if you write it down, or they get it out of the book, they haven't learned it, they haven't produced it at all. And so what you really need to do is have them write down what the rule is. Obviously, you can look at the book and stuff like that, but when they make this should be what comes out of their mind. And usually, after you've done a few easy examples, you can do stuff like this. X squared x to the 5th, or x squared x to the 7th, and they'll be able to tell you x to the 9th. You say, why? Well, there's x squared. There's x to the 7th, right? This just means you're timesing x by itself 7 times. That means you're timesing x by itself 2 times. You times them together and you have 9 of them. There's 2, there's 7, altogether there's 9. X cubed, x to the 5th. Well, that's x to the 8th. You have x cubed, x to the 5th. Altogether there's 8 of them, x to the 8th. This column is almost more important than this one. So, some examples that they may need to really know. Something like that, where it gets a little bit more involved. And finally, this is where you are actually helping the student get closer to the subject. Textbooks are written. They're not always going to have you next to them to interpret the textbook, and so they've got to learn how to do it themselves. This helps them bridge the gap. Putting the book over there, not the same as the rule. They really are the exact same thing. In fact, this entire row is the same thing. But if they can understand, oh yeah, I'm adding exponents, over here they're like, oh, when I'm timesing this together, I'll add those together to get a new number. But they're not exactly the same variables, so we're putting them together. We just have to write as m plus n. So that's why rule and book have to be 2 different columns, and it helps them to see, that's what they're saying. Whenever you times 2 things together, they're alike like that, that's what the book is meaning. You're now adding them. Good thing to put in this column are non-examples, such as x to the 5th times y to the 8th. You can't combine them anymore. They're done. This only works if they're the exact same, because this 2 and the 7, they give you the entire thing. Only if these are all the exact same. You can't have 2 y's and 7 x's and have anything multiplied by itself 9 times. Another good one is to make sure they realize these rules only work if this is multiplication. If you are timesing them, you don't do anything with this at all. And we'll come up with that a little bit later. So, the next rule. On this particular one, x squared to the 5th. You may need to come up over to this column before that and say, okay, x squared, we got to do this 5 times. 1, 2, 3, 4, 5. How many total do we have? 2, 4, 6, 8, 10. We have 10 of them. Notice that when you do the next one, x cubed to the 7th, or any other example you want to, you say, what do you think that is? They're going to look at that and they're going to say, I think it's 21. You say, why? Well, you just times them. You should realize that that is a golden moment in tutoring. That is when the student just told you the rule. You didn't. The student did. And that means the student is learning it. So, again, examples, 3m to the 6th to the 8th. Yeah, that's 3m, whatever's there, to the 48th power. So on and so forth. And fill out all of those rules. In particular, when you get down here to, you have this, that's in the book one. So you've got this one down here where you're going to have a to the m over a to the n equals a to the m minus n. This will actually be the basis, if they really believe that. 5th, and again you're going to have x to the 5th left. They get the idea of subtraction. Well, that's going to help you when you do this to them. Okay, following that rule, what is that guy? And they're like, well, 2 minus 7 is a negative 5. And you're like, okay, do it over here. Uh-oh. They have just come up with the definition of a negative exponent. The other thing that it helps you with is when you have x to the 5th over x to the 5th. Well, by this rule up here, that better be x to the 0. X to the 5th over x to the 5th, anything over itself equals 1. So this is a really fun one to do examples on. They think they're getting away with something. 2x squared times 3y to the negative 7th power, all to the 0, and it equals 1. And they're like, what? How do you know that? Well, you're like, anything to the 0 power is 1. It's good to do some of those examples. So that will be their developmental process for exponents. And you'll be surprised at how well just going through and making this with them, summarizing everything on one piece of paper will be later on when you're doing polynomials, stuff like that. It'll be really, really helpful. In particular, the next thing that we're going to be doing with polynomials, books will try to tell them adding polynomials is something new. This is something you should fight against. When you are adding polynomials, all it is combining like terms. Which is interesting. When we teach arithmetic, Math 100A, and we talk about like terms, this is how we start. 5 sheep plus 3 sheep. Well, obviously that's 11 sheep. How about 2 apples plus 7 apples? Well, that's 9 apples. What about 5 sheep plus 7 apples? Equals what? And they should give you a funny look. 5 sheep plus 7 apples is 12 what? Doesn't make any sense. It shouldn't make any sense. Addition is only defined if you have like things. You take 2 apples, 7 apples, great, 9 apples. Notice that this that you are adding remains the same. It is the 2 and the 7 that actually combine. So when you're doing 3x squared plus 5x plus 9, and you are adding that to 7x squared minus 11x plus 2, they should note that these are the things that are being added. You have 3x squared and 7x squared, that's 10x squared. And in this context, they should see it as the same thing, just like 3/7 plus 2/7. 2/7 is 5/7. These are the things that you're adding. That's why you need a common denominator. They need to be like things. Otherwise, addition doesn't make sense. So 10x squared minus a 6x plus an 11. That is the step. It is combining like terms. There's nothing else. There is something that they may find really good, and that is to say, okay, just like when we add numbers and you line up the decimals so that the hundreds and hundreds add up, 300s and 200s is 500s, we do it the same way here. So this is the column. 3x squared plus 7x squared, that gives you 10x squared. So minus 6x plus 11 gives you the same thing. They will like this vertical format because it looks exactly like what they've been doing with decimals. Now, for you tutors, I would not suggest doing this with your students often, but you should note that in particular, if you took this problem where x equals 10, this is how we write bases. This would be 359 plus 700 minus 11 tens, which is 110. So it's 592. This problem and that problem are the same thing if x is 10. These are simply placeholders. Remember, we have the ones column, the tens column, the hundreds column, the thousands column. A polynomial is actually a generalized version of what we do in our decimal system. So don't tell your students that. They will not appreciate it. Now, multiplication. Most of you have run across a little statement called FOIL. You should understand that FOIL is not a mathematical operation. It is an acronym helping people remember a mathematical operation. And that's very different. For example, when I teach multiplication, let's get this off. When I teach multiplication, of polynomials, it is an extension of the distributive property. For example, I take 3x times x minus 7, x squared minus 7x plus 2, and I'm able to jump it in. They can do this without much of a problem. 3x cubed, again, you're adding exponents, minus 21x squared plus 6x. They're fine with that. I change this up a little bit. If they really understand the distributive property, it shouldn't matter what's in here at all, not even a little. So they could do something like a square. Well, that's going to be square x squared minus 7 square x plus 2 squares. In fact, I do a squiggle to make sure that they really have this down. That would be a squiggle x squared minus squiggle times 7x plus 2 squiggles, or squiggle times 2. Okay. If they really get this, then I should be able to go x plus 11 right there and have them come up with the following. I should be able to take x squared times x plus 11 minus 7x times x plus 11 plus 2 times x plus 11. Now note that that thing can be simplified down. You get this x cubed plus 11x squared minus 7x squared minus 77x plus 2x plus 22. And yes, it gets long. Oh well. They will have to get over that. And doing this a couple of times, they will. Now, this is what's interesting. The concept of multiplying polynomials is that this guy came from that times that. This one came from that times that. And so on. Every single thing in this will have to touch everything in that. That's where we have 2 things here, 3 things there. That's why we have 6 terms. Well, certainly they can combine, and you'll teach them that. But that's the crucial element. The reason why FOIL isn't so good to teach them from the beginning is because, try FOIL on this thing. Great, there's our front, there's our last, but we have 4 middle terms right now, not just an O and an I. So, for those of you that are not familiar with it, if you are ever multiplying binomials, you can use it. Let's write this down. First of all, when you're multiplying polynomials, really, combine like terms. That's it. 2 steps and you're done. And they can always remember that. So, for those of you that aren't familiar with FOIL, if you jump the x in and make sure it hits each term in the other side, you have x squared minus 9x. Jump the 7 in, you get 7x minus 63. Now, the reason FOIL is valuable is to remind them not just to go, oh, x times x is x squared, 7 times 9 is 63. We're done. That helps them remember that the front 2 times together is there, the outside 2 times together is there, the inside 2 times together is there, and the last 2 times together, their product is there. FOIL. So it's kind of nice, especially if they get something like this. They will have learned those exponent rules really well. And they'll want to write x squared plus 25 because the 2, like when you wrote this, oh, you're like, hey, yeah, that's 25x squared. It's exactly like this. The big thing about polynomials that makes this requisite is the plus sign. Let me highlight that. This is the crucial thing. When you are multiplying these 2 together, if you had 7x times a negative 9x, you would get a negative 63x squared. You need to get behind the students misunderstanding. If they just write, oh, x squared minus 63, they'll say, I thought that's just, didn't we just do something like that? What you have been doing in timesing them together has led their brain to believe that. And there is a crucial difference, and it is the plus sign. These are monomials. These are binomials. Anything that is a polynomial more than a monomial has a plus sign in it. And that throws everything off. That makes it completely in a different realm than just multiplying two monomials together. Multiplication is commutative. You can just move these around, and that's where you get the negative 63x squared. When you have this plus and the minus sign, here's one term that has to hit these two separate terms. Here's one term. It has to hit two separate terms. You are no longer just doing one problem, you're actually doing four. Or in the one that we had earlier where we had 2 times a 3, you had 6 different problems that you were doing. So in this case, this falls in the second category where this is x plus 5 times x plus 5. So the way I use FOIL is when they do this and they write x squared plus 25, I tell them you forgot to FOIL, which means they forgot to make sure each term here in the first one hit each term in the second one. That's where we get x squared plus 5x plus 5x plus 25. And there you have it. That's where they get the middle 10x from. Which means you ought to try it with them sometime. 2x plus 3 to the third power cubed. Say that plus sign, as much as you would like it not to be there and make it an easy problem, that plus sign just made this a really tough problem. Where this has to hit each one of these, and you get a product. And then every one of that has to hit each of these two. And that's multiply each term by each in the second. So I think that will finish up exponents.